Hello, everyone. I'm Vijay Sundaresan, and I want to thank you for joining this webcast. I'm a senior technical staff member at the IBM Toronto lab, and I work on WebSphere and Java performance. I'll turn it over to Tom, my co-presenter, to introduce himself. Go ahead, Tom.
Hi, my name is Tom Watson. I work in the IBM lab in Austin. I've been working on Liberty for the past 10 years or so, and I'm the lead developer on Liberty Instant On.
Thank you, Tom. So today's topic is, as Tom alluded to, a feature called Instant On that we've added to the Liberty runtime. And what we're hoping is that this talk introduces you to the motivation for why we did this feature, how the feature works, as well as convinces you that this is the answer to Java's long-standing startup problems. So Java is not a language that's known for starting up quickly, but we are positioning Instant On as a solution for the problem of rapid startup without compromise for cloud-native Java applications. Now, a few disclaimers before we get going here. I am talking about a beta feature here in Liberty, as well as there's going to be some performance data that's presented here. So these disclaimers are just to make you aware that some of those results may vary by environment, as well as some of the statements we make around the beta feature looking ahead aren't actual release commitments. So with that caveat, let's move ahead. So the first place I'd like to start is around the motivation for this feature. So cloud native is not just a new fad. It's a revolution. Really, it changes how application developers write applications, how those applications get deployed, how the cost metrics around running these applications in the cloud. So it's a whole different world from the world of on-premise monolithic applications. It's a completely different experience that the end user expects. And it should be no surprise, therefore, that there are more demands placed on application frameworks and the underlying JVM technologies. Now, what are some examples of this? The frameworks can't just treat themselves as a runtime for running Java applications. They also have to help developers be more productive developing cloud-native applications. This is very different to developing monolithic applications, for example. And one example of that is that when you write a microservices application, you may have to interface with other microservices applications in order to test it. And how do you facilitate something like that? That's a problem you just didn't have in the old way of doing things. Also, from a cloud agility perspective, you may be required to release your application several times a day. And that may be a problem that you haven't encountered before. You may have different demands in terms of monitoring your application and in general, interfacing with the container technologies that underpin these cloud platforms. And finally, from an operational efficiency perspective, on the cloud, you get charged for everything. Oftentimes, the public cloud charges you by memory used, by the amount of CPU used, or some combination thereof. And so the framework the Java frameworks and the JVMs have to help businesses reduce costs and achieve their sustainability goals. Which brings us to Liberty. Liberty achieves all of these goals and more. But for those of you who are not familiar with Liberty, I suspect a lot of WebSphere customers are already aware of it. But those of you who are not, it is a lightweight open framework for building fast and effective cloud-native Java microservices. Now, Open Liberty as a project has been out there as an open source project for the last 5 years or so. So there's a lot of good material that you can Google for and obtain, getting started guides, technical deep dives, videos, etc. There was also an excellent talk done last week on this platform, which is almost like the precursor to this talk, which is a deeper dive into Instant On specifically. But that earlier talk done last week was titled Liberty Cloud Native Without Compromise. And I strongly suggest that you listen to that talk to get a a broader perspective into the strengths of Liberty overall. Now, obviously, that was a full hour-long presentation, but I did want to just quickly mention some of the things that were presented there, because it underlines Open Liberty as a premier runtime for running cloud-native Java workloads. So, as I said, cloud native really affects all phases of the application development lifecycle, and the picture on the right shows that there's planning, coding, building, testing, etc. And I'll be talking about all of these different stages in the life cycle on this slide, and giving you a taste of what Liberty has to offer in those different areas. First and foremost, Liberty is developer friendly. What does this mean? It allows you to configure the runtime very easily, the framework very easily. There's a simple text file that allows you to select many different configuration parameters. It also allows you to select just the right number of features that you want. So you don't have to bring in all the features that are there in the specification along. You can pick and choose the features that are necessary for your specific application. Liberty has also done a lot of work to integrate very well with popular IDEs and make the task of developing Liberty applications a joyful one. There's a mode in Liberty called dev mode, which allows you to write your application, save them, and dev mode will detect those changes and basically launch testing, create a container for you, and run it so that you can, it automates a bunch of those tasks that you would have to do manually otherwise. And finally, Liberty is a very versatile runtime. It allows you to run applications that adhere to many different specifications. So Jakarta EE applications are supported, Java EE is supported, microprofile applications can be run on Liberty. And finally, this may surprise you, you can even run Spring Boot applications on Liberty as well. So extremely versatile and developer-friendly in that regard. On the agility front, there's a very capable and very beneficial Liberty operator that facilitates and automates many tasks that are specific to your Liberty applications. This can be used as an extension point on top of the OpenShift framework that exists that already automates a bunch of operational tasks. But using the Liberty operator, you can get specific tasks related to your Liberty applications automated as well. Now, it's also designed for continuous integration and delivery to support that cadence that you may have of having to deliver an application several times a day, for example, as well as there's easy and simplified setup if you want to run Liberty on the leading clouds like AWS and Azure. And IBM Cloud. Now, there's also a feature called zero migration, which basically means that you don't have to worry about your applications that were written earlier breaking when you pick up a new version of Liberty. Liberty preserves the zero migration or provides a zero migration guarantee, meaning that when you pick up a new version of Liberty, your existing applications will also will continue to run in exactly the same way. Now, we talked a lot about all those other boxes, but really the focus of this talk is around that run box that's highlighted on this slide. So what does the run box mean? It basically equates to how you're running your applications on the cloud, and that invariably comes down to lower operating costs. One of the main reasons we've heard from customers for why they've migrated to the cloud is to save costs. And of course, Liberty has some exceptional performance characteristics, which we worked very hard over the years to build, that make it an excellent Java framework to save costs. So in particular, it has world-leading throughput, meaning fewer instances need to be launched for the same workloads. You can get more done out of one JVM running Liberty server than you can with other application servers or frameworks. Fewer instances, in turn, means lower infrastructure and support costs as well. We've also shown results, or I've done talks in the past, and you can Google around Open Liberty performance. and get data around lower memory footprint as well. This is not just lower memory footprint just after starting up the application, but also during the period when load is applied. So not only does Liberty deliver better throughput, it does so while taking lesser memory, meaning those public clouds that charge for memory and CPU, you're covered on both fronts. Liberty is an excellent runtime from both metrics. Okay, but what we want to talk about in this presentation is actually driven by a different sort of tactic that users employ on the cloud, and that's driven again by how cloud economics work. Fundamentally, cloud providers offer a pay-as-you-go pricing model based on CPU and memory use. So businesses that are built on the cloud need the ability to scale up or down to meet varying demand. Now, this is a different sort of tactic to just picking a runtime that has good memory and throughput characteristics. This is less about what's running inside the container, but more about how you can scale up or down different instances or instances as demand changes. Now, the requirements in order to support this sort of scale out and scale down flow are that you need to have low memory usage. So when you add new instances, you shouldn't add more memory use than you need to. And also, when you want to bring up new instances, that should happen really quickly so that you can handle requests with minimum amount of latency. So this means in turn that fast startup is important at all levels. It's important in the Kubernetes layer, it's important at the Knative layer, but it's also important in the Java frameworks themselves. And that's where the rest of this talk will go. This is the motivation for why we chose to improve the startup time in Java frameworks using this instant on feature. So let's look at a typical work flow as a new request comes in to a serverless service. So if no pods are running, a request comes in, and then this is reported to the autoscaler, which invariably is Knative. That's one of the popular infrastructures out there. And then that starts a minimum number of pods that you configured in order to handle this request. Now, those pods come up, they start handling the request. And then when requests go down, the autoscaler also decides when it's time to scale back down to 0. Now, if this process repeats n number of times as demand varies through the day, having a high startup time overhead, and by high, I mean here really over a second is what an end user might discern from their perspective. Now, this includes the time to start up the application, but also to start up a new container and to handle that first request for that user to get a response back. All that has to be around about a second. And if you have a framework that starts up in several seconds or tens of seconds or 20 seconds, this is probably not good enough in order to be satisfying users in a serverless scenario. So the one way to work around this sort of thing could be to keep an instance running, at least one application instance running all the time, rather than scaling down to 0. But then this requires additional cost and overhead associated with that one running instance. So this is why super fast startup is important. It's not just enough to start up in a few seconds. You have to be able to start up in a few hundreds of milliseconds. And the Java community has done a lot of work to satisfy this sort of requirement, because this is a new requirement, let's put it that way. In the long history of Java, the JVM was designed with other goals in mind. Basically, bytecodes were loaded in the JVM and optimized as the application was running. There was a JIT compiler. This was the traditional way in which Java applications were run. However, this leads to the reputation that Java has, which is slow to start up, but really good from a peak throughput perspective. Now, the community hasn't stood still. They have woken up to this new use case. the need to have these sorts of super fast startup times. And there's been innovation in some areas. You may have heard of the Graal project that produces a native image for Java applications and allows you to obtain those kinds of really fast startup times. However, there are some trade-offs between running in native image mode and in traditional JVM mode that you may or may not be aware of. And so I'll discuss those a little bit. So the picture on the right shows kind of where we think these two differing points on the spectrum are. So from a startup time perspective, undoubtedly the native image approach scores. It's able to start up applications really fast, but it doesn't do quite as well in terms of peak performance. And this is because it's basically building a statically compiled image. So it loses some of the runtime information that would have allowed us to get excellent peak throughput performance. Also, the amount of time that it takes to build a native image can be quite substantial. It can take you several minutes or even more than 10 minutes to build an image in certain cases, and that doesn't jive very well with the continuous integration deployment sort of mindset that users want or have in the cloud. There's also the footprint itself of the running application, and it's really there isn't all that much to choose. One thing I will say is that while native image strips out parts of the application that aren't in use, it also doesn't have quite as mature a garbage collection technology as a traditional JVM does. And so this can lead to footprint differences down the line when you're running actual load on the server. It can also lead to differences in terms of pause times that can be something that customers are sensitive to. And finally, the last but not the least, the biggest difference I would say is in terms of usability. Graal VM, the native image, does require some adjustments. There are a set of limitations that you can read about if you Google about it. Notable amongst those being that you can't load classes dynamically. You have to take certain actions to compensate for the more dynamic features in the language like reflection, etc. So there are some usability drawbacks in the native image, which are obviously not there in the traditional way of running applications, where the JDK or the JVM adheres to the full JVM specification. This is where the feature that we're talking about today comes in. So Liberty Instant On. What do we hope to achieve with Liberty Instant On? First of all, what is it? It's a holistic solution that provides fast startup without compromise. By holistic, I mean that the solution encompasses not just the Java framework or the app server itself, but it extends down into the JVM as well, or the JDK as well. I'll talk a little bit about the JDK in use here called Semeru runtimes and give you an introduction to that as well next. But fundamentally, Liberty Instant On uses this Linux technology called CRIU. This is a technology that can be used to freeze a running process and then restore it from where we froze it. So what is the benefit from a startup time perspective? Basically, what we can do is we can run an application up to a certain point where we take the snapshot and then, or where we take the checkpoint, we freeze it. And then when the time comes to deploy the application, we can pick up execution from where we left off or where we froze the application. We don't have to rerun all the code that ran before we took the checkpoint. We can pick up from where we left off, and that obviously means we're doing fewer initialization tasks than we did in the traditional JVM run. Now, as I said, this is a holistic approach. It does require, it's quite a wide-ranging feature that does require support from the JDK layer as well. This is because Liberty is up at the Java framework level, and CRIU is down at the operating system level. And so you need the JDK to kind of bind those two layers together. So the JDK that we recommend running with Liberty, that the JDK that you get with Liberty containers is this JDK called Semeru runtimes. So it's a production-ready JDK based on the Eclipse OpenJ9 JVM. The OpenJ9 JVM is also the JVM that was powering the IBM JDK 8. So if you're using that JDK, it's the same JVM underneath it. And OpenJ9 is generally known for being very well tuned to the cloud, has fast startup, low memory use, and also has broad platform support, including, in particular, the IBM platforms. IBM Z and Power are also covered there. And there are zero usage restrictions around using Semeru runtimes. So when we talk about Liberty Instant On, at other times in the presentation, we may refer to Semeru Instant On, and that the two are sort of stacked on top of each other. So Liberty Instant On is a Liberty feature, and it leverages the Instant On feature in the Semeru JDK that goes under, and then the Liberty framework is running on top of. So the Instant On feature in the JDK provides sort of or explores this third alternative, as I said, between static compilation and traditional JVMs, and it uses this checkpoint restore technology offered by Linux CRIU. In particular, it provides fast startup while keeping the benefits of traditional JVMs. So essentially, we're hoping you can have your cake and eat it too. It permits operations like dynamic task loading. It has a mature JIT and GC that has been developed over the last 20 years. It doesn't have any closed world assumptions, and you can run existing applications and libraries unchanged. Those are some of the design goals we have with this feature. Now, the picture on the right shows the difference in how this is how a traditional run works and how a run with Instant On works. In the traditional case, you start up an application and it runs, the JVM starts up, the application initializes, and then you're ready to serve requests after that, and you've initialized the framework at that point. With Instant On, we split up that traditional run into two phases. There's a build phase where we'll run the JVM startup and the application initialization, and then take a checkpoint at that point. And that concludes the build phase. Now we've taken this checkpoint image and we can put it into the application container image. And now when we are deploying that application, Liberty will pick up on the fact that there are these checkpoint image files, and we'll just start running from that point on. So it'll initiate a restore, which essentially picks up from where we left off. So there's a little bit of overhead to start up and recognize that you're doing this restore and do some of the tasks related to getting ready. But once that's done, you basically continue on and serving requests and avoided all that initialization altogether. So that sounds great. Obviously, removing a bunch of computation altogether from the deployment environment can only help with startup time. But how much does it help? So this graph shows the results that we've got with our current prototype of Liberty Instant On. So it shows 3 applications that we tried. The first one is a very simple REST application called PingPerf. It was starting up in a second and a half originally. With Instant On, we improved that startup time by 10x, got down to the 130, 140 millisecond range. The second one is a slightly more complex application. It's called REST CRUD, which has a database access in it. And again, in this case, we were able to achieve a 10x speed up and get down to that 200 millisecond or so range. Finally, the third application is an Acme Air microservices application. So this is a microprofile application. And this is more interesting in that it's doing a greater amount of computation. There's more business logic here. And again, in this case, we're able to start up well under 500 millisecond. I think it's closer to 250 milliseconds in this case as well. So really excellent results that we're seeing with the prototype, fulfilling the promise that you don't have to give up on the programming model, that you can still use all the features that you want to and still get this terrific startup time. With that, I'll turn it over to Tom to continue on from here.
Thanks, Vijay. So now that we've established the promise of Instant On, I'd like to go into a little bit more details on how Open Liberty Instant On is leveraging the Semeru technology and CRIU in particular in order to do a checkpoint and restore solution. So our goal is basically to provide a seamless solution where developers can use this as part of their build of their application container image. And the way we do this is we provide three specific points in our startup process on where you can take a checkpoint. And they're basically, at three different points, features as being the lowest point, or the earliest point, rather, that you could take a checkpoint. And the earlier you do the checkpoint, the less you're going to get as far as speed up on your restore time. So down at the features level, that's where we, in the Liberty kernel, are loading up the features you have configured. So like Vijay was saying, we're a fit-for-purpose runtime. So if your application only depends on CDI or JAX-RS, you only have to enable those bits of our functionality, and we'll only load those up, so we can provide that quick startup at that level. Obviously, the more features you enable for your application, perhaps you need the full Jakarta EE stack, that's going to take a little longer to start up. It can take up to like 2 seconds. So that features phase can get rid of that overhead. And basically that's happens after we've loaded up all the features and got them started and ready for processing the configured applications. So the next phase is what we call deployment. This is where we actually now start looking at the applications you have configured, processing their metadata, class annotations, and so on, basically getting the Liberty container ready to service your application. But at this point, we haven't actually run any of the application code. That comes in the next phase, which is what we call applications. And at this point, potentially we'll start running some of the early startup code of your application if your application has such things. Like, for example, early start servlets that can get started during the application starting in order to initialize themselves. CDI beans can also get initialized early if they're listening for notifications about application scope initialization, as well as servlet container listeners and servlet context listeners. These types of things can get invoked and run during your application startup, and they can do a number of initializations for your application. So depending on your application, that can take quite a long time. And then for other more simple applications like the ping-perf one Vijay was mentioning, have no early startup code. So that phase is quite fast. But that's the very last phase that we allow for you to do the checkpoint. This also is before we open up any ports that would be used to service your application. So we prevent any initial incoming requests from happening on the checkpoint side. And the reason we do this is because we view this as sort of a build step, and we don't really want you to consider having to do incoming requests in order to prime your application container image. We want this all just to happen in the normal, whenever you're building that container, not having to make any additional requests to it. The other things we want to prevent is allowing for that application to make external type of requests to outside resources, such as databases and such. These types of things would create states within the checkpointed image that we wouldn't be able to successfully restore when we're talking about restoring that particular application into many different instances, perhaps all running at the same time in order to scale up your application. So some of the things you have to consider is, well, the later you checkpoint, obviously, the faster the restore time is going to be, but also it does increase some of the complexity and some of the things you have to consider. So, for example, if your application is doing quite a bit of work in its early startup, some of that stuff may not be able to work quite as well or be successfully restored when we're talking about restoring in the cloud. So some of those things are when you'd have to fall back to, say, the deployment phase so that we can avoid running your early startup code during application container build. So with that in mind, I do want to go into the container support. So our incident on support, we do view it as the primary use case being in container. And there's several different reasons for this, but the primary reason is that in order to successfully restore with CRIU, CRIU validates that all of the resources that process was using are still available and in the same state that they were when you did the checkpoint. And if they're not, then it'll fail to do the restore. So in a container, we're able to tightly control that because each layer is locked in place. So the layer that contains the checkpointed image will be constant each time you're restoring that particular application image. So the first step to using Liberty Incident On is to build that application container image. So in this particular slide, I have a typical Docker file, but that's used for Liberty containerized application. But the one difference is I'm using the Open Liberty beta checkpoint image. So this is an image that we produced and is published today that contains the prerequisites that are needed in order to do a checkpoint with CRIU. So it contains the CRIU binaries, it contains the Simaru runtime that Vijay was mentioning, and then all the other tools that are necessary for us to be able to do a checkpoint in container. So when you build your application with such a Docker file, it's not actually going to do any checkpoint at this time. It's just going to create the original application container image. And then the next step would be to go ahead and add a layer on top of that that is going to do the checkpoint. So the way we do this is by using Podman to run that particular application image that you just built, but then you're passing some additional parameters in order to do the checkpoint. So here I'm passing in this WLP checkpoint, and I'm telling it to checkpoint add applications, that last possible phase. The other thing I want to mention is for doing the checkpoint, we are using a privileged container. And really, this is just the easiest way to give CRIU in the container all the necessary capabilities that it needs to do the checkpoint of the Liberty process. This is only on the checkpoint side whenever you're building up your application container image. As I'll show later, that you don't actually need a fully privileged container when you're doing a restore. But what this ends up doing is it starts up the application, and Liberty is doing its normal startup process. But once we've started up the application and before we've opened up any ports to take incoming requests, we ask CRIU to go ahead and take a checkpoint. And we actually ask Simaru, the JVM, to do the checkpoint for us, because it'll do a bit of work for us before we to get the JVM and Liberty ready for that checkpoint. And after it's completed, CRIU will actually terminate the process, and then that'll in turn stop the actual container. So what we're left with is a container that has an additional layer on top of that original application image that contains the process image that CRIU created. So the final step is to commit that image into, commit that container into an image that includes the checkpointed process. And the way we do that is through a podman commit command that just takes your container name and commits it to your specified application image name. And finally, in order to be able to restore, we just do your standard podman run command. There are some additional Linux capabilities that I'll go into later that you have to specify to allow CRIU to restore. But at that point, what happens is Liberty will recognize that that image is there for the process, and it will actually restore from there, and it does that very quickly and then gets into the rest of the startup process, which is basically just open up the ports and start listening for incoming requests. So the next thing I'd like to do is go into a demo. So let me share my screen. Okay, hopefully we see this just fine.
Yes, I can see it.
Okay, let me just minimize this, get it out of the way. Okay, so the first thing I'm going to do is just go through that step where I create the application image. So this particular example, I'm using the Getting Started guide for Open Liberty. So this is just a fork of that, but some of the things I've changed is the Docker file itself. The only change I made here was, again, changing it to Open Liberty Beta Instant On. Before it was just using, the Open Liberty full image. The next step is just to build the application. So I have a script that does this. This just is doing the podman build command, and I already run this, so it's just getting everything from the cached that I already built. But now I have a Getting Started image that doesn't have a checkpointed process in it. I can run this original image. So this is just doing the podman run, and it's bringing up the actual application from the very beginning in the container. And then you'll notice it comes up in just under five seconds. So this is really just a simple REST application that gets the system properties and basically just displays them. Nothing very complicated. We do enable a number of other things like metrics and health and other things that contribute to the overall startup time, and elevate that to right around 5 seconds. But the next thing I want to do is take that application image that I created, and I want to go ahead and checkpoint the process in that container and then create that instant on container image on top of that. So I have a script to do that. And it's just, like I said, going to do the podman run, and it's going to run the Getting Started image, but I'm going to pass the applications option to it to do the checkpoint add applications. So let's go ahead and do that. So like before, when I was running the application image, Liberty comes up. But then once the application has reported that it has started, we ask CRIU to go ahead and do the checkpoint of the process. And then in turn, it asks CRIU, which eventually checkpoints the process, gets that all saved into an image file, and then kills the process, which in turn the container is terminated. So now I have that container that's stopped with the process checkpointed. And then the final thing was the commit. So now I have a Getting Started instant on container image. So if I look at the images, it's going to be hard to see, but I have the container image here, and then the original one that I had already created is here. So if now I can run the instant on one. Well, let me first show you what the instant on is doing. So the additional capabilities I had alluded to before, that these are capabilities that CRIU needs in order to restore the process. So one of them is the checkpoint restore capability. This is a capability that got added to the Linux kernel in version 5.9. And it was explicitly added for CRIU so that we could reduce the set of capabilities as needed. Prior to this, you had to grant full sysadmin capability, which is provides for a very wide range of things to grant into the container and allow CRIU to use. So this reduces that drastically. Additionally, CRIU still needs the sysptrace option to be able to restore successfully. And then we also need netadmin for some functionalities from the JVM and Open Liberty dealing with the network. But then you just start it as normal from the getting started instant on image. So let's go ahead and run this. So again, this is just going to pick up right from where we had done the checkpoint, and then we get started in right around 400 milliseconds. So typically, depending on your system, we usually see 10x or better. So if you remember, the prior one was right around 4 or 5 seconds. Now we're down to about 400 milliseconds. I didn't. So the application still, works. If I kill it, it's going to stop working. So we can continually, restart this application. It's just going to keep starting up the time. And as you notice, that now it came up in 200 milliseconds. So it obviously primed some of my disk and got it up faster. So that's running in container. But now I want to sort of show this running in a Kubernetes environment and using something like Knative for doing auto scaling. So I do already have a Knative instance running. Right now, it should have no pods running because I have both the original application image as well as the instant on application image have been deployed into this Kubernetes environment with Knative. But I have it such that it'll quickly scale down to 0 in like 30 seconds or so. So the pods don't stay around very long if you don't have any incoming requests. So I have a couple of scripts that'll just force some requests. So let's do the, I'm going to invoke the original application. So this one is, again, going to have to fire up that pod for the original application, as well as the overhead for Knative to do all of the auto scaling stuff. So if we see this going, this is where Knative starts picking up, and now it's actually trying to start up that pod for the original application image. So this does take quite a bit of time. It usually takes around 13 seconds. Here it took 13.6 seconds to come up. In this particular environment, my Knative overhead seems to be right around 3 seconds or so. So 3 seconds of that is really attributed to that auto scaling, and then the remaining 10 seconds is Liberty. Now, if I do the instant on invocation of this, it's going to be much faster. So right around 3.8 seconds. So again, 3 seconds of that is Knative and Kubernetes. So if I need to go ahead and try and get the logs quickly. So before these things go away, that one was already terminating, but that's the original one. That didn't work. Hold on. Hopefully my hasn't gone away yet. Okay. So yeah, so that one came up in 700 milliseconds. The original one, it looks like it came up in 11 seconds. So it's quite a drastic drop. And as you can see with the actual invocations of them, they're both probably terminated. So I'm just going to invoke the instant on one again. And so now that one already got terminated. So it has to take the additional overhead again to get it started. But if I keep requesting now, it's instantly responding. So that's the end of my demos, but I hope it demonstrated quite well how much faster we can start up with the Liberty instant on. So I'm going to go ahead and hopefully I stopped my sharing and hand it back over to Vijay.
Thanks, Tom. So in the remainder of this talk, what we'll do is actually dive down into the actual implementation details a bit more, give you a sense of how this is working under the hood. And for that, I'll start with the basic support that we added to Semeru, the CRIU support API. Now, as an end Liberty application developer, you probably don't even need to know about this API, because this is an API that's offered by the JDK up to Liberty, and Liberty uses this API to control CRIU. So as the picture on the right shows, the application sits on top of Liberty. Liberty uses the checkpoint JVM impl API offered by the JVM. The JVM in turn interfaces directly with CRIU through the native API that it offers. So all these tasks that that need to be done to compensate or to overcome the way CRIU restores the process are handled for you transparently by Liberty and the JVM. And that's the beauty of Instant On. So what are some of these, or what are some of the options available to you using this Java API? You can configure CRIU in different ways. You can control it to enable different levels of logging so that you're able to debug what happened with your restore. You're able to select the image directory. You're able to select if you want to do a privileged checkpoint restore or an unprivileged one. There's a whole host of options that CRIU allows, and the Java API that we offer, this CRIU support API, tries to mirror that so that Liberty can take advantage of that. The API also offers helpful error codes in case something went wrong. Okay, the next piece of support that I would like to highlight from a JDK perspective is this notion of hooks, or pre-checkpoint hooks in particular on this slide. But what is a hook method in general? A hook method is basically a method that we use that will respond to certain events. So if you're about to take a checkpoint, that's an event, and you can register your hook methods to respond to that event. And when Liberty is about to take a checkpoint, about to request a checkpoint from CRIU, these hook methods can be run on demand, essentially, to prepare your Java application to be checkpointed. So this notion of pre-checkpoint hooks exists. So let's say the picture on the right shows your application threads are running. At some point, Liberty decides to initiate a checkpoint. After that, there's only one thread that runs. So there's this notion of a single-threaded mode that we enter once we've initiated a checkpoint. And in this single-threaded mode, we allow both Liberty and JVM hooks to run to perform various compensations. Now, I'll give one example of what that sort of compensation could be, is to close some file handles that may be open, so that you don't have to worry about the contents of those files when you're restoring. CRIU fails to restore if the contents of the files that it has open have changed. So in that case, so in order to avoid sort of unnecessary restore issues, you can close some file handles that you no longer need. And similarly, there's a mirror image notion on the restore side. So there's a set of hooks that you can register to run once the restore has happened. Invariably, the restore hooks follow a reverse sequence to what the sequence in which we did the checkpointing. We'll run things in sort of the reverse order. So we'll run JVM hooks first and then Liberty hooks. All of that happens in single-threaded mode. And then we let the other application threads run. At that point, this would be let Liberty get back to the task of running the application. And one example of a task we could do in the post-restore hook could be to reopen one of those file handles that we closed and I talked about in the pre-checkpoint hook. So what are these hooks used for at a high level, though? The different kinds of compensations that need to occur to account for CRIU's unique behaviors or the ways in which it restores the process. The JDK and the app server take charge and help sort of paper over some of those issues so that as an end user, you're not exposed to them. So what are some of these issues? Basically, it all boils down to the difference between the environment where the checkpoint was taken versus where the restores will occur. The checkpoint environment could be quite different to the environment where the restores occur. It might have different environment variables. You might be restoring at a very different point in time. There may be different security requirements or configurations that you might want to support at deployment time. So it needs to handle all those tasks seamlessly and work with CRIU as limitations to sort of provide a seamless end user experience. Now, I'll get into 3 examples here, but I won't spend too much time on it. The first one is around compensating for environment variables. So when I talk about limitations of CRIU, one of the limitations is that it freezes the environment variable space to be what it was when the process was checkpointed. What does this mean? Any new environment variables that you added, any changes to existing environment variables that you wanted, these are not going to be detected because CRIU restored the process with the environment variable space as it was at checkpoint time. So how can you configure the application to pick up sort of deployment environment variables in order to specify, let's say, a port or a server address for a database or for tracing or other things like that? So what we offer is that there's a file that Liberty can specify the name of the file in which you can specify these environment variables, basically. So instead of relying on the environment to get these values, we pick them up from this file. It's really easy to set all the values that are not, it's really easy to set new values for environment variables. It's really easy to add new environment variables. And it all sort of gets picked up by the JVM and the right behaviors occur. Now, the way there's some limitations in the JVM in that we can't create an environment variable representation, use it as part of the initialization sequence that ran at checkpoint time, and then suddenly come along later and change that environment variable. So any environment variable that was used during and up till the point of checkpoint, you cannot change those environment variables. If there's an environment variable that wasn't used up until the checkpoint time, that one can be changed. We can pick up a new value at deployment time. So on the right, we show some examples, basically. So if you had on the top, you have an environment variable N1, and it has a value 1. We can change that value or add a new environment variable N2 with value 2, and that would get detected and picked up if it was in this file. Similarly, if you have N1, which has a value 1, and it's a mutable environment variable, then if you change that value, that change in value also gets picked up just fine. The case that won't work is if you had a value 1 and it was already queried before checkpoint time. Now we don't allow changing that environment variable, and if you try doing that, we provide an exception that tells you that you've tried to do that. Now, one other thing, Liberty itself, the restore script makes an attempt to scrape the environment variables that it sees at restore time and put them into a file that the Semeru JDK can then read. So it facilitates this task of creating a file that the JDK can read and pick up new environment variables for. Similarly, there's time APIs, and what is the problem with the time APIs like nanotime or current time millis? Basically, the problem is that the time between checkpoint and restore is counted towards elapsed time. So the consequence is that a large amount of time could have appeared to have passed between taking the checkpoint and restoring it. When you build your container image, maybe a long time in the past compared to when you restore it and deploy the application. So in order to help with this sort of time delta that exists between checkpoint and restore, what we do is we do various compensations in the JDK itself. So especially around APIs like object wait, nanotime, unsafe park, all have been changed to compensate and subtract out the time period between checkpoint and restore. This allows you to see basically that period between the checkpoint and the restore doesn't appear anymore, and it allows you to run your application as though that period didn't even exist and you were just running the application continuously from start to end. Now, current time millis is a different API which requires a certain absolute notion of time. It's the amount of time that started since or has passed since the start of the epoch, a date in 1970. So we can't just arbitrarily go and change that value. And this can lead to some complications if you're measuring relative time across the checkpoint time. That you may still get the elapsed time between the checkpoint and the restore still getting counted if you're using current time millis across this sort of boundary. But you can get around that by using, say, nanotime, or if you're no longer using current time millis across that point. And the final one I'll say is, as I'll talk about the compensation, is around the random classes. So random is a class that in the Java class library that gives you a random sequence of integers or longs, of numbers, basically. And what you don't want is for these random number generators to be initialized with the same seed. And because then every time you restore from that particular checkpoint, you'll get the same random number sequence. So you want to preserve that sort of entropy that you need in order to provide certain security guarantees. And the way the JDK helps with this is that it goes in and reseeds these random objects on restore, which means that they all get different seeds, as I've shown in the figure, the right, and therefore they produce different sequences of random numbers as is required. With that, I'll turn it back over to Tom one last time.
Sure. Just for the interest of time, we only have like 2 minutes left. So I think instead of going over, I was going to go over a little bit more detail on the checkpoint, but I don't think that we have too much time to go into that. So I just kind of like to get to summarizing this all up. So we really view this instant on technology really helps Liberty step into this serverless use case. Liberty is already quite versatile runtime and has really been geared for cloud deployments for a long time. It's been a premier runtime for the cloud. But now with Instant On, this is kind of a key capability that allows us to step into the scale to zero type scenarios. So in order to continually drive the adoption into cloud, we need to be able to evolve our development, our deployment, and our cloud runtime. And we feel that Instant On is just going to enhance Liberty that much more and allow for you to still utilize all of the great benefits of the JVM, but still be able to have that Instant On behavior. So with that, I just want to conclude. Thanks for attending our talk. If there's any time for questions, go ahead and post them now, and we'll try to answer them now or perhaps at a later time. So Vijay, I don't know if you have any last minute. That's pretty much the end of our talk.
Yes, I did want to draw attention quickly to the links on the right. These materials will be provided later. The slides will be provided later. There's also some blogs that have been written about this capability in the last few weeks. So if you Google Liberty Instant On or Semeru Instant On, you will get quite a few hits.
There is a quick question on which version of Liberty. This is available for beta right now, so we don't yet have a confirmed time when we would GA this, but you can try it out right now in beta form, and we are, really wanting to get feedback from anybody using this and how they're using it with their application. All right, we're at the top of the hour, so thanks for joining. That's the end of the talk.